So let us take stock. We are dealing with the expression of a particular gene which exists in two alleles, two forms, uppercase A, which is dominant, and lowercase a, which is recessive and lethal. The corresponding genotypes are three in number. The normal homozygous, comprised of two uppercase A's, the heterozygous carriers, an uppercase A and a lowercase a, and the sadly diseased individuals, two lowercase a's. Let us say that in the mating population, in the general population at large, that these individuals are in the proportion U to 2V to W. U represents that fraction of the populace whose genotype is normal and homozygous, in other words, two uppercase A's. Twice V represents that proportion of the population which is heterozygous, in other words, an uppercase A and a lowercase a gene in the genotype. And W represents the sick individuals, the individuals which have two lowercase a's in their genotype. So, for instance, if 60% of the population is normal and homozygous, 30% of the population is heterozygous, and 10% of the population is diseased, then U will be 0.6, twice V will be 0.3, and W will be 0.1. Why twice V, you ask? Purely for algebraic convenience. It's going to turn out that as we do the calculations, we are going to eventually get a stray factor 2 in the denominator, and it'll be nice to cancel it out and give us a nice clean compact answer. We could just as well have left it as V instead, and then we'd have to carry the 2 somewhere else. But bear with me, this will simplify the algebra just ever so slightly. Now, let's move on from the picture of the general population to that portion of the population that is engaged in mating and creating progeny. If an individual is infected, has two lowercase a's in the genotype, they die early and therefore cannot mate. In other words, two lowercase a genotype individuals are forbidden from mating. In any case, our setting is as follows. We start with an overall population, and of this population, only a segment, the normal homozygous and the heterozygous, who are carriers but do not show visible evidence of the disease. They themselves are not sick. These are the only individuals who are allowed to mate. For simplicity, we're going to assume that both sexes have these genotypes in the same proportions. Now, if this is the case, let's consider the setting where we had 60% of the population was normal and homozygous, 30% was heterozygous, 10% was infected. Then the 10% of infected individuals cannot mate, and that leaves 90% of the population who can mate. Of this 90%, 60% are normal and homozygous, and so they comprise 60 out of 90, or 2 in 3, or 2/3 of the whole mating population. And the heterozygous individuals, the carriers, comprise 30 out of 90, or 1/3 of the mating population. Of course, what I've just described for you is just a simple exercise in conditional probability. What we're really asking is the following question. If we remove the sick individuals from the population, and we select an individual at random, what is their genotype? There will be normal and homozygous from the mating population with a probability of U divided by 1 minus W. The factor 1 minus W in the denominator is just renormalizing so that the smaller subset of mating individuals now has got unit size. Of course, this is just conditional probability, right? What we are saying is U over 1 minus W is exactly the same as U divided by U plus 2V, because U plus 2V plus W is 1. Likewise, the proportion of individuals in the mating population who are heterozygous is twice V over 1 minus W. All right, so our original probability distributions are now adapted slightly to take into account this new circumstance that sick individuals are unable to mate. Now, in this mating population, we still have the two genes represented. We have uppercase A and lowercase a through the carrier. Let's keep an eye on the frequency at which the dominant and the recessive and lethal genes appear. If one selects a gene at random from a selected individual who is mating, well, if that individual is normal and homozygous, it will certainly be a dominant, normal, uppercase A gene. But if that individual is a carrier, then half the time that will be a normal gene, and half the time it will be the recessive and lethal gene. Let's introduce a little bit of notation and keep this at the back of our minds. Right. So the experiment is as follows. We pick a random individual, male or female, from the mating pool, which means that they are either normal and homozygous or heterozygous, and we select a gene. We're looking just a little bit ahead because in the mating process, each individual will confer one gene to the progeny. So if you pick one gene out of the pair which makes up the genotype, then that gene will be dominant with probability 1 if the individual was normal and homozygous. It will be normal with probability 1/2 if the individual were heterozygous. Sum the two together and we get the proportion of the dominant gene in the mating population. Likewise, if from an individual who mates you select a gene, what proportion of the time is that gene recessive and lethal? Well, it cannot be recessive or lethal if the individual originally had a normal homozygous gene, because that individual does not have a lethal gene to proffer. But if that individual were a carrier, and their genotype was of the form uppercase A and lowercase a, then half the time among the heterozygous proportion of the mating population will a lethal gene emerge. Let's call P the fraction of the dominant gene in the mating population, and let's call Q the fraction of the lethal gene in the mating population. Of course, P plus Q must be 1. Now, this gives us a goodly setting to start with. Our next step, of course, is to put individuals together and consider the mating process which leads to progeny and the passing on of hereditary characteristics.